with these diagrams, I was wanting to prove to you that you can't put a line, you can't intersect lines through an ordinary point. You can't intersect ordinary lines to an ordinary point. And I'll start with this one right here. This is a 9-sided polygon, and you intersect at every node where there's 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes. So for this graph, it intersects. There's 4 right here, 4 right here, 4 right here, 4 right here, and 4 right here. Each one of these with a 4 on the ends of it is a 4, 4, 4, 4, 4. This is the fractal line that it creates going through. What I mean by fractal line is that with a 9-sided polygon, if you intersect all the nodes with every single other one of them, then you create these lines, these 4 lines, parallel lines to each other going through at these angles. This is an 8-sided polygon, and if you notice, it has 3 and 4 and 3 and 4 alternating. If you connected every single node to every other single node, it creates these lines, these fractal lines, parallel to each other. 1, 2, 3, and 1, 2, 3, 4, and 4. And they intersect 1. That's a 3 right here. 3 of them side by side, 4 of them side by side, 3 of them side by side, 4 of them side by side, 3 of them side by side. And if you expand this out, you would see that these lines are actually fractal lines that make up the intersection of these points. These fractal points is what I call them. Same thing with this one. This has 7 sides to it. And if you connected every node, 7 of them, to every other node, it would be 3. Just like 9 was 4. 8 was 3 and 4 and 3 and 4 and 3 and 4. Well, this one is 3 and 3 and 3 and 3 and 3 and 3. There's 3 parallel lines, fractal lines going across from each other, cutting through this way. 3 cutting through this way. 3 cutting through that way. 3 cutting through this way. 3 back again cutting through this way. And if you go to 6 nodes, 1, 2, 3, 4, 5, 6, and you connected them to every single one, and you drew lines through them, you'd have 3 and 2, 3 and 2, 3 and 2, just like 8 was 3 and 4, 3 and 4, 3 and 4. You'd have 3 lines parallel to each other. I call them fractal lines again. And then at this angle, you have 2 parallel, and then 3, and then 2. Okay, then right here, and all these are labeled off-center. It's off-center if it has an opening. It's centered if there's an intersection at the very center. Off-center, centered, and this is off-centered again, opening. And this is 2, 2, 2, 2, and 2. And this is a 5-sided polygon. You have 2 going through parallel to each other. 2, 2, 2, and you see why I'm called it off-center, because it's off-center from this whole shape. These lines, these fractal lines cutting through here. Now we're down to a square, or a 4-sided polygon. You have 2 intersecting nodes, or 2 fractal lines parallel to each other intersecting at this angle. Then you have 1, and then 2, 1, 2, 1, 2. and this is centered. It has a point in the middle where it intersects, and then this is off center again, a triangle, and it's now you can really see why I call it off center. It's off center, doesn't cut through, and this has 1, same as this is at 1 2 1 2 1 2. This just has 1 1 1 1. Same as this had 2 2 2 2. Same as this had 3 3 3 3. Same as this had 4 4 4 4. And this had 3 4 3 4. 3 2 3 2. 2 1 2 1. And now 1 1 1 1 1 1. Then you go from the triangle to a line. Is it 1 or 2 lines? Well, it could be both, because they immediately follow one another. So it could be 2 lines adjacent to each other, which is not quite a plane, but I'd call that a fractal, evidence of a fractal nature. You could have 2 lines, and then you could have 1 line, and both of their fractal nature would be, their patterns would be 1 0 1 0 1 0, because they intersect here, but they don't intersect here, and don't intersect here. And so this is why I conclude that no line can pass through an ordinary point, because if you follow this whole train of logic and geometry, graphic geometry, I guess, yeah, 4 4 4 4, 3 4 3 4, 3 3 3 3, 3 2 3 2, 2 2 2 2 2, 2 1 2 1, 1 1 1 1 1, 1 1 1 1 1, and 1 0 1 0. So that would leave a point as an ordinary point as a 0 0 0 0. That's next beyond 1 0 1 0 0 0 0 0. So on an ordinary point, no lines can pass through it. And that's why I call for fractal points. Fractal points. Anything that has any sort of a node system to it. And fractal points, unlike normal points, can grow from an ordinary point, which is a subset of a fractal point. It's a node of these fractal points. And they can grow from a point to a line to a triangle, or to 2 lines adjacent to each other, to a triangle, to a square, to a pentagon, hexagon, 7-sided, 8-sided, 9-sided. They can go on indefinitely. So a point can grow. And I think this seems more logical to me than a point. I never believed that you could actually pass a line through a point. There's no physical basis for it. But with these fractal points, you can pass fractal lines through them. Fractal lines adjacent to each other. It's more like with the wave nature of the best descriptions we have of reality so far. More like wavy lines than actual lines, and more like fractal points than actual points. And this is one way that you can get rid of infinities. Instead of having a point, you have a fractal point. And this could be an image of a fractal point. And this is a fractal point where it intersects it with itself. And that's that hologram bow is a idea of a fractal point, except it's visual. And this is a fractal point with 8 sides to it, and this this is a cutaway of a fractal point with 8 sides to it right here. But this has many more. And these ideas can be extended to invisibility and holography and other things. And it's all because if you consider the point nature of space to actually be fractal points, they create a boundary between the virtual reality inside and the reality of our world outside of its boundary. And these they produce other virtual mirror worlds. And I think a fractal point makes more sense than a ordinary point. Thanks a lot.